Hi, my name is Hwan. I'm a PhD student at Stanford, finishing up my program this year. And I have worked on the cosmic microwave background telescopes called BICEP array telescopes. So I joined the group in 2013, and then the first deployment of BICEP3 to the South Pole was during the season between 2014 and 15. And so I joined the group to get everything right for BICEP3 to work. Yeah, and I worked on data quality checks and whatever needs to be done for BICEP3 that we work together as a group. I mostly work on data analysis these days, and towards the final year of my PhD, we actually did something different with BICEP3. During the summertime of 2018 and 19 season, we used the BICEP3 telescope to observe at a different elevation at the South Pole from what we usually observe, the CMB polarization. So BICEP3 and Keck array are the telescopes at the South Pole, as you can see here. And it has a little bit of history there too. So this is the South Pole station. And we land on a plane on this skiway to get to the South Pole Station. And the South Pole Station has two major buildings for the CMB astronomy. And in this building called MAPO, we had Keck array telescopes for quite a long time. And Keck array telescope actually consists of 5 copies of BICEP2 grade telescopes at different frequency bands. And soon this Keck array will be replaced with BICEP array, which will be 4 copies of BICEP3 sized telescopes, also at multiple wavelengths. And the reason why we need multiple wavelengths to observe the CMB is to distinguish the CMB from other components of the sky signal that we can get. And in the other building is where BICEP telescopes have been. So BICEP1, the first generation BICEP was there from 2006 to 2009, and BICEP2 after, and then BICEP3 since 2015. Yeah, so I mostly spent time with this BICEP3 during my PhD studies. Yeah, of course, the South Pole is a great place to observe the cosmic microwave background. It's very dry, and the atmosphere is very stable, and you get continuous night of 6 months with little variation of the environment. So it's a really great place to observe the CMB. And of course, since the sky doesn't change, it just spins above your head, you can access to the patch of the sky you want to observe continuously year-round. ESO and BICEP Keck array collaboration, they are all looking at the CMB, the cosmic microwave background, especially the polarization signals, to test the theory of inflation, which tells that at the beginning of the Big Bang, the universe has started with expansion, which is really, really fast, exponentially expanding universe, which would leave some imprints on the much time later on the cosmic microwave background through the effect of gravitational waves propagated from the inflation. So, yeah, they're both observing cosmic microwave background to find out whether we had inflation or not. Kind of a huge evidence if we see it. Both ACE-SO and BICEP array, their common goal is to map out the cosmic microwave background polarization very deep so that you can find the faint signal of inflation. But last year, during the summer season at the South Pole, we tested some more possibilities that BICEP3 might do, which is to put our telescope a little bit away from where we have been digging in to find the faint signal, but to test some extended area coverage below the elevation that we used to observe. And below a certain elevation, the telescope couldn't work properly cryogenically. That was the reason why, one reason why we didn't go below that elevation. But also, if you go below the elevation of some degrees, you have to go through a lot of atmosphere than higher elevation. So it's not as fast as you would observe at higher elevation to dig into deeper faint signals. But the low elevation fields at the South Pole may be high elevation at the site for SO, because SO is located at the Atacama Desert, which is more close to the equator of the Earth than the South Pole, of course. So it can access to more area of the sky at a different elevation range. And one interesting patch that's below the usual elevation we observed at the South Pole is the CMB Cold Spot. So in the temperature map of the CMB, a cold spot was first identified by in a WMAP data set by a Spanish group. And it's a particularly large area of the cold spot. So you see there are many cold spots there. And if you expand this area where the CMB cold spot is, you see this temperature map. And you see there are other cold spots and hot spots, but in particular, this is a special case given the level of coldness and the size of the spot. So based on how you characterize it, the statistical importance of identification of this cold spot is around like 1 realization in 50 realizations of the full sky. So if you have a randomly generated, Gaussian anisotropic universe, if you make 50 of them, you may find one of these. So is it just a statistical fluke, or is it something that can explain the coldness? That's the question that we want to answer. And that was asked by other people, and many people have tried to explain it by their own theories, and also they also developed potential methods to distinguish certain hypotheses to explain the cold spot. So what we are trying to do with BICEP3 is to get a better measurement in polarization, so that the theories and the methods that distinguishes the explanations of the cold spot, the coldness of the temperature, may be followed up by the observation of the polarization. So if the anomaly exists in polarization as well, what should we consider about this spot? Or if there is no corresponding anomalous in the polarization, should we try to include more exotic theories that can explain this coldness of the cold spot? So our test observation is going along the way to that goal. What part of the sky that we did observe with BICEP3? So, so this is a full sky map observed by Planck, 353 gigahertz, and then so it's it's closely showing the galactic plane of where the dust is strong. And this highlight area down here is the usual observing patch by BICEP3. But the cold spot is below the elevation that we used to observe. Cold spot is at about 20 degrees elevation at the South Pole. So we pointed out to a different patch of the sky with the mirror to redirect our beam to the low elevation. So this is the new spot that we tested. And here you see the cold spot over there. And the important area of the polarization measurement that we need to make to distinguish those hypotheses is especially like the 7 degrees ring around the cold spot. And probably you can also take data up to 20 degrees ring around the cold spot and use the information to distinguish those hypotheses. And we first tested with this patch of the sky that's accessible by BICEP3, as you can see in the thick black contour.
Great. And so what did you find?
So we found that so there were previous studies, like for example, potential theory to explain the coldness is from supervoids, like lack of material along the line of sight to the cold spot at rather late time of the cosmic history, because that may cool the CMB light along the way it reaches us. So their study found some, they did a survey of galaxies towards this spot and estimated how much that will cool down the cold spot. But they couldn't explain all the drop of the temperature. And also Planck satellite has polarization data as well, but it was not sensitive enough to meet the other people's criteria to use polarization data to distinguish those hypotheses. And with BICEP3, it has a lot of detectors, and its high sensitivity at degree angular scales give fast observation possible. So within only a month of observation, it can get deeper than what Planck obtained in this area of the observing patch. So the thing that we are looking for is the correlation between the temperature of the cold spot and the E-mode polarization around the cold spot. So we demonstrate that we can take a picture of the E-mode within this patch. Yeah, so we're continuously digging into this field with BICEP array, which is really more powerful than the Keck array. So by that, we'll have stronger power to distinguish whether the B-mode polarization signal we see in this patch, how much of it is coming from the actual CMB or the other foregrounds that's, sending signals to us between the CMB and us somewhere. Like galactic dust or synchrotron radiation, we'll be able to have better data set to distinguish those things. It was very fortunate that I could do a bit of side project with BICEP3 during the summertime that we don't usually do our regular CMB observation to test what BICEP3 can do, and in some sense pushing the limit and confirm what we can do, and also think about something not just the CMB polarization generated by the inflation that we usually think about, but some other projects that we can do with our data set.